Thank you for joining us this afternoon. My name is Bob Abramson. I manage the marketing for Waltron, and I'm really happy that you guys could spend a little time with us on our first of our SWAS webinar series, Troubleshooting Stator Coolant. Before I introduce the presenter, a couple of housekeeping items. Everybody, when they jump in, should be on mute. We ask that you please stay on mute to avoid the background noise. Hopefully we'll have a few minutes at the end of the presentation for question and answers. So if you could just type in your questions in the comment box, I can go through them at the end of the presentation. And yes, I will be sending out a link where you can view a recording of the program. You'll get that by next Tuesday. I'll say you'll have that in your hands, along with some links to some other additional resources that Lukas is going to mention during this presentation. Without any further ado, let's get to the presentation. Waltron, and you folks are lucky to have Lukas Staub handling this presentation. Lukas is our Chief Commercial Officer, and he's an engineer by training, although he's been in the water chemistry game for 20 odd years. And he joined Waltron at the beginning of this year. We're really lucky to have him, and we're excited that he's here to present to you all today. So without further ado, I'm turning it over to Lukas. Away we go.
Thanks, Bob. So welcome everyone to this first webinar. My name is Lukas Staub, as Bob mentioned, joined Waltron at the beginning of the year or December last year, and happy to go on with this first seminar on troubleshooting stator coolant chemistry issues to avoid potential failures. The presentation itself is a case study, but I'll give you a little bit of background on the stator coolant chemistry, a little bit of the setup of the plant that some of this work has been carried out. The presentation and the webinar itself is going to focus on the monitoring of stator coolant chemistry. There is a couple of references that I'm going to make in due course of the presentation. And one that I'd like to mention at the very beginning, there is another seminar held by IAPS, the International Association for the Properties of Water and Steam, on the 27th of May. That is more in-depth of stator coolant chemistry itself, not really the monitoring aspect of it, but the chemistry itself. So what we're going to do today, we're going to have a look at the system design a little bit. We're accessing the technical challenges of maintaining stator coolant chemistry. Some of this is design-based. That's why we're going to have a look at the system design of water-cooled generators and stators. Critical risks in copper-bearing units. Improper chemistry will lead to corrosion, of course, oxidation, corrosion, and that could impact the heat flux greatly by plugging of conductors, and the consequences of it is a potential catastrophic failure in the generation. Very important part of that, kind of giving us a bit of a chemistry overview and giving us some monitoring options, how we can make sure that the chemistry is right. Okay. There is, as mentioned, a few references to be made. The key related technical publications, the IAPS TGD and the chemistry of stator coolant chemistry, that's available on IAPS. IAPS is a worldwide based organization. It's nonprofit, so all the technical guidance documents are actually for free. The IAPS, just to mention a little bit what IAPS is, I mentioned in the beginning, International Association of the Properties of Water and Steam. The technical guidance document was actually published or approved in Banff at the conference, at the annual conference in Banff in October 2019. And again, it's free to download. IAPS in general, the next very important meeting that is going to come up is the meeting in June. That's going to be the IAPS Power Cycle Chemistry Group. It's open to anyone. David Addison is the contact. He's the chair of the Power Cycle Chemistry Group. And he also contributed largely to that, actually to the case study that I'm going to show later on that particular plant in New Zealand. So let's dive in. Thermodynamics of the copper oxidation. Like in many systems that in power plants that are water in contact with water, we're trying to passivate. We're trying to form a stable layer of copper oxide in this particular case. And there is like dual phases of stable layers of copper oxide. One is the low dissolved oxygen regime. We're talking about lower than 20 ppb, which is forming that cuprous oxide. And the other one is a high DO, where we're talking about higher than 2000 ppb, which is then forming a cupric oxide layer as the dominant oxide. And anything in between is going to be a very high risk. So manufacturers specify generally what the kind of like regime that you have to apply. And the danger, and I call this the dangerous middle, it's that oxide destabilization. So anywhere in between those two ranges of dissolved oxygen in the stator coolant, you will face a destabilization and therefore like corrosion product forming that then again can the aforementioned or cause the aforementioned clogging of your coolant system. In very simple terms, you want to avoid that dangerous middle, so you want to control your oxygen levels very reliably, either below those 20 ppb or above these 2000 ppb. Now getting into the case study. So we're talking about a 250 megawatt coal-fired power station here. It's been commissioned in 1980, copper-containing stator, of course, and the design basis is that low oxygen neutral pH regime that I mentioned before. This is a typical one that we want to be below that 20 ppb range in dissolved oxygen. The incident trigger was a repeated drain and refuel cycle during the return to service after a major outage, and obviously small air in leak from pump seals that made it difficult to maintain these low ppb ranges of oxygen that we required for this particular case. And what we saw then is a frequent blockage of the stator coolant filters due to the copper oxide transport. And that was then followed by concerns with this condition that there could be a potential overheating and catastrophic failure of the generators. So what we explored a little bit was how do we measure oxygen in such an environment? We're talking about a closed loop, we're talking about pressure, and we talk about a solution or a sample that is highly, I'll call it contaminated by hydrogen. It's not really a contamination, but it's just a high amount of hydrogen that is present in that particular cycle. In this particular cycle, if you try to measure oxygen with a well-known Clark sensor, a amperometric oxygen sensor that has been proven good working in many of the power plant applications, and especially for very low detection limits, you will see that most of these sensors are prone to an interference with the hydrogen ions. This interference will lead to a false reading, so to speak, and causing a significant drift in the total, or can actually also mean a total signal loss. Especially in these applications, there is a little bit of a maintenance burden on such sensors, and it's also difficult to remove them from the process, which again, this is a process where we have pressure, we have a certain temperature applied, and removing the sensor for just maintenance purposes is a bit of a burden. There can also be interferences that are from temperature fluctuations and mechanical damage in particle. This is especially mechanical damage to the membrane that usually covers a Clark cell. The methodology that is applied in this particular case to find if it would be more suitable was the luminescent dissolved oxygen measurement. It's a dynamic luminescence quenching. It's very well known, meanwhile, in a power plant environment. The general detection limits allow us to go below 1 ppb meanwhile, so far enough for an application where we're looking to maintain oxygen levels below 20 ppb. And because we don't have a hydrogen interference, we are actually much more stable, and there is no drift in the measurement. So the 0-point calibration that has to be done is a not very frequent. And again, I remind you, we're not measuring close to the 0 points. The process is very simple. An LED excites a luminescent dye on the sensor. The dye emits a red light, the fluorescence light, and then the oxygen molecules collide with that dye and quench. And so with the quenching and the time shift, there is a proportion to the amount of oxygen pressure present. So very simple technology applied. And because we're not looking at a membrane, well, there is a sort of a membrane, obviously, in such a sensor that contains the luminescent dye, but this is a ceramic membrane, if you will, which is much less prone to mechanical damage. Obviously, if there's particles around, there is no disturbance to be expected from the pressure or temperature shifts. So much more stable measurement. So the technical advantages, actually, I mentioned already quite a bit of that. One of the most important one is the H2 immunity. So there is not going to be any hydrogen interference in the measurement. Also, there is a flow independence. Unlike in amperometric measurements, LDO does not consume oxygen, is not impacted by the sample flow rates. Now, sample flow rates under normal circumstances in an online measurements are relatively easy to control, so it doesn't really matter. But in this particular case where you have a sensor in line, flow dependency does matter. And so you don't have that with an LDO measurement. And sensor spots typically last up to 4 years, especially in applications like this, where you can time the pulse so that the sensor spot gets more durable, which means if you only have to exchange that sensor spot every 4 years, that's fairly low maintenance, I would say. And then there is a greater stability with the LDO measurement. The zero drift or the non-existing zero drift ensures that the measurements remain accurate in that low ppb range, below somewhat 20 ppb. The implementation of real-time diagnosis for this particular case with the corrosion products that were transported clogged up the filters and were impacting the Stator Coolant flow was kind of like center of the diagnosis. So knowing in real time what the measurements really looked, or the oxygen contents really looked, revealed that there was indeed 100 to 2000 ppb in which represents that unstable transition zone between the two different stable oxide layers formed below 20 ppb and above the 2000. And so we could easily track on the oxygen, but now there needed to be some resolution to where is this high oxygen content coming from. But it correlated basically with the filter changes. So whenever you change the filter, better flows, and then an oxygen ingress would lead to that middle layer there between 100 and 3000 ppb, where we actually did not want to be. So as corrective actions, there was a procedure installed that is an offline nitrogen sparging. This was initiated to strip the excess O2 to get back below those 20 ppbs where we wanted to be. And then a feedback loop on the LDO analyzer provided instant feedback on that sparge efficiency, which was a good result to see with the LDO, seeing that oxygen level dropping down below the levels that we were actually requiring for this particular installation here. So as a result, we were able to re-establish low oxygen, neutral pH as per the initial design within hours. Chemistry was stabilized and holding the formation of transportable copper oxides, corrosion products, so to speak. So in essence, a constant luminescent technology provides proactive mitigations and also a strategy where the galvanic sensors failed due to their hydrogen interference that are prone to. And trustworthy data, as always in monitoring of water steam cycle chemistry, it kind of eliminates that blind spot. So you're not running a Stator Coolant chemistry in that danger zone where you're not supposed to. So with the availability of a reliable oxygen measurement, that actually pretty much solves the problem. And should you actually move into that area where you have to remove oxygen actually from the Stator Coolant chemistry, that gives you an instant alarm if you're exceeding the levels that would be allowed. Online DO analysis is only as good as it is resistance to interference, which is, again, why choosing the LDO is the right thing to do in this particular case. And this plant in particular gained visibility, the visibility that was basically needed to save the generator from a catastrophic thermal event. And with this, I conclude the short presentation, and I hope we're having a lot of questions now, Bob, and happy to answer those questions as far as I can.
Okay, so let me see. I see one came through across. Again, if you have any questions, you could put them into the chat box. I'll see them there. Or if you want to raise your hand, I can call on you, and then you should have the ability also to take yourself off mute. The one question I have here is, does the type of oxygen regime have any influence or input on whether you would go with the anapyramic or the luminescent technology? The example that you gave, I believe that was a low oxygen regime. Would that make a difference or not?
It does make a difference in terms of electrolyte consumption or Clark cell. Generally, Clark cells for lower measurements for lower ppb ranges of oxygen have very small deposits, very small amounts of electrolyte. And this is what gets depleted, and it gets depleted faster the higher the amount of oxygen is. So if you put a Clark cell with the same amount of electrolyte in a 20 ppb environment versus a 2000 ppb environment, it's going to last much longer in the lower end. And so the oxygen sensors, the Clark cells in the higher regime, are actually going to be very quick to deplete. The other problem with the higher end is that the measurement itself, can be done quite precisely, and the reproducibility at the higher end isn't mattering so much. But the presence of hydrogen at these high levels is probably even more of a problem than with the lower levels. So in both ways, the LDO is the superior technology for that kind of monitoring task.
So luminescent sounds a lot more flexible, besides the fact that it seems like it's less, you don't have those membranes, you know, the electrolytes and everything. Okay, thank you. That's pretty clear. Anybody else have any other questions for Lukas? Again, you can feel free to take yourself off mute and speak up, or you could enter a message into the chat box to the right, lower right-hand corner. We'll give it a minute here. So is the anapyramic, the Clark cell, that's an older technology? I believe it is. Anyways, why would someone choose? It doesn't seem like there's any reason to choose that. Why would anybody go with that technology?
I guess the main decision would be price driven. Clark cells have a tendency to be cheaper than LDO sensors for good reasons. So I guess that is really the only thing. But again, if you're having a technology deployed in a water steam cycle, or in this particular case, in a closed cooling water loop, basically, that is not suitable to reliability tech, price doesn't really matter.
Sounds like, it's not the biggest price driver of obviously these analyzers, but I would imagine it's cheaper on the front end maybe, but like in the back end, doesn't the Clark cell have more consumables and more maintenance required? So the total cost of ownership may be in the favor of luminescent.
They are definitely in favor. Total cost is definitely in favor of the luminescent technology, not really because of the price of consumables and replacement membranes and all that sort of thing, but consider the labor that is involved in like exchanging the membranes, taking a sensor out of service, and also considering the amount of time where you're offline with that measurement, and again, creating that blind spot that we were supposed to eliminate with the measurement. Yes.
Makes sense. All right. Okay. Last chance again.
Yeah, I've got a question.
Thank you. Who are you?
Nathan Schuster.
All right. Thanks.
Besides a nitrogen purge, what other options would you have in a situation like what you described? Like, could you add chemistry like bisulfite or something like that to this sort of a system?
It's difficult to give you a general answer to that, because in this particular case, the nitrogen sparging was really kind of like the only option you have. Depending on what kind of chemistry you run through the Stator Coolant, you might have an option with a scavenger as well, but I would be very cautious about that. If you talk to chemical companies that supply oxygen scavenger chemicals, they might give you advice to use those. But again, it depends a lot on what is your ratio on oxygen and hydrogen. So very difficult to make a general statement here. What the best resolution is to get rid of the excess oxygen in the plant. It's very individual.
Okay, thanks.
Thanks for the question. All right. Anybody else? Feel free to take yourself off mute and ask Lukas.
I have a question. Hi, this is Niso from the Stator company. Lukas, you were telling us about low oxygen systems. Like in our company, all our Stator cooling water systems are high dissolved oxygen and neutral pH. Is there a benefit to install dissolved oxygen probes in these kind of systems? And if so, what would be the benefit?
Thank you for that. I actually didn't quite understood. Your regime is all low oxygen, you said?
High oxygen.
Oh, you're high. You're on the high side. Okay, now the question makes even more sense. If you're in the high oxygen, you have a different monitoring task, quite simply. You want to make sure that you don't fall below that 2000 ppb or whatever your lower limit is actually going to be. Again, the danger zone is somewhere between 100 and 2000, and that's where you don't want to be. So if you're running a high oxygen regime, you want to make sure that you really are above those 3000 ppb. And again, the oxygen measurement is the indicator that tells you whether you're in the right spot or not. And I'm guessing also, if you're running high oxygen regimes, you're actively dosing the oxygen?
No, it just whatever comes with the makeup water supply that we feed from the surge tank, what we feed, demineralized water supply, and pretty much that.
Okay.
No, we do not add oxygen. It just whatever is in water already.
Okay, so you have that oxygen introduced, and once you introduce that oxygen, you assume it is a closed loop and there's no oxygen going in, nor is there any oxygen going out.
Yeah, Lukas, I have another question. In terms of installation configuration, those dissolved oxygen probes, are they sitting in pipe, or there is like a loop, kidney loop with a flow cell?
It can be both, actually. It depends a little bit on the pressure and temperatures that you're having in that specific loop, but it can be both. It can be mounted inline, and it can be mounted on a bypass loop. What you don't want, of course, is a sample that like an online sample, like what you do in a water steam sample panel, where you have a sample actually extracted from the process. That's definitely not what you want. But we see both. We see that people like to have a bypass line that actually goes back into the process, just so you can isolate it for maintenance purposes. But other than that, you can actually put it directly in the loop.
Thank you so much.
Thank you.
Excellent. Great question. Okay, once again, feel free to take yourself off mute and ask a question if you have it. We'll stay on for a couple more minutes, as long as we get questions coming in. All right, you can see that to the left of the screen, info@waltron.net. If you get a question and we're out of time and you come back and you say, oh, I wish I asked this, go ahead and fire that question to that email, which is pretty easy to remember. Again, I will be sending out an email with, it'll have a link to the presentation, links to the resources that Lukas shared with you today. And if you receive that and you have a question, by all means, respond to that email and we will definitely follow up with you. It looks like we're out of questions, Lukas. Thank you so much. It's some great participation, and really appreciate you making the time, and for everybody that joined us for making the time and spending a little time with us and learning something new, hopefully. So
Thank you very much.
Okay, guys. Have a great rest of your week.